Coming out of your first exposure to physics, a lot of times you might think that the normal force is just another way of talking about gravity, but it's up instead of down. And that's because most of our questions we talked about looked something like this, where you had an object that was on a horizontal surface. And in these cases, it is true that the normal force does equal out or balance out the force of gravity, m times g. But there are many situations where that's not the case, and we'll see more of them in our class. For instance, in this situation over here, we have someone pushing down on the block, so there's an applied force, maybe P. And then there's also, of course, the weight, mg. And so the normal force is going to have to be big, something that's big enough to balance out both of those forces. The normal force will equal our applied force P plus mg. Or maybe we have a situation like this one down here where the object is underneath a surface. Now that seems kind of strange, but it is possible that maybe someone is pushing an object up against the surface. Well, the weight of the object always pulls straight down, and in this case, since the surface is above the object, the normal force would also point down. And so we would have to exert enough force P to sort of balance those two things. This situation here, where we have an object that's perfectly vertical on a vertical surface instead, our normal force would point to the right. Here's a really odd situation because weight is down. The normal force has absolutely no connection whatsoever to the weight. So that's something we'll have to get used to. And then lastly, let me mention a situation where a block is on an incline. And this is something we'll spend an entire little section on. But here, of course, your weight is down, but your normal force points like this. It's perpendicular to the surface. And so we're going to have to treat that with a little bit of extra care because not only are they not opposite to each other, they're not even along the same line. Let's take a look at an example of where this is going to come into play. So a good place to start on a question that involves a number of forces is to draw a free body diagram. So we would think about that box's mass being squashed all down into one little point, and then we would start labeling some forces. Anywhere there's contact, there's going to be a force. So we would have this pulling force, maybe we call it F sub t, that's at an angle, theta. We have a normal force, that's what we're talking about here. And that would be upward since our surface is down below our object. And then also because there's a surface in contact and there's mention of friction, we would include that. Our object is going to be moving to the right, and so our frictional force working against that sliding motion is going to be a kinetic friction pointing to the left. And then lastly, the force that doesn't need contact, that's the gravitational force pointing down. And so what we would do here is we would consider all of these forces, but we would consider them in terms of what's pointing horizontally and then what is pointing vertically. And so any force that points vertically, those are going to have to balance out because our object doesn't actually move. There are these two forces, F of n and mg, that are shown here. But there's also an upward component of the tension along with a horizontal component of the tension. And so we're going to have to break the tension force into two pieces so that we can use it within our calculations. Give myself a little more room here. All right, so let's look in the y direction. All the forces in the y direction actually have to balance out. They're going to have to equal 0 if I take into account their direction. So that means that F of n plus this component upwards, that's going to be the hypotenuse times the sine, so F of t sine of theta. That all pulling upwards is going to have to equal the weight that's pulling down. If I go through and put some numbers in here, F sub n plus my tension force is 160 times the sine of 25. That will equal the weight down, which is 20 times 10, or 200 newtons. when we go through and do this, we should get 132 as our normal force. So a little bit less than the weight itself. Then if I switch directions and I look at the x direction, I should be able to find my acceleration. These forces don't add up to 0. They add up to the mass times the acceleration. Again, thinking about the direction of things. Since the acceleration is to the right, then I'm going to choose the rightward force to list first. That's my positive force. So that would be F sub t times the cosine of theta. Working against the motion is the frictional force, and friction is mu times the normal force. So we'll put that in as mu times F sub n. And together, that all determines the mass times the acceleration. Again, putting in some values here, I have my tension of 160 times the cosine of 25 minus mu has a value of 0.2 in the problem. And then I'm going to use this normal force that I just found, 132. Mass is 20, and then times A. And this comes out to be about 5.9. Again, key points to this problem. You gotta make sure that you're looking at the everything going on in the y direction, everything going on the x direction. Keep all of your components separate, solving sort of two problems within one. All right, this second question, I'm not actually going to go through and solve completely. I just want to point out some differences that we would see. So because the boy is pulling somewhat down on the rope, my tension force would look something like that. I would still have the weight force of mg. That looks like a 35, 55 here. I would still have normal force, but since the tension force has a component to the right and a component down, I expect my normal force to be much bigger than in the last problem, because the normal force is going to equal the weight plus the component of tension that's pulling down. And then, of course, I would have a frictional force as well. So you would go through and do the same sort of setup as you would in other situations. But again, paying attention that your applied force or your tension force is somewhat down. If you want to pause the video for a second, I am going to post the solution here so that you can see it, but give you a chance to try this question on your own. All right, so hopefully again you pause the video and tried it on your own. Key things to notice again is that this step changes a little bit. You got to look at your picture, use that to determine how the up forces are going to balance out the down forces. And then also notice here, played around a little bit with the angles. You certainly could use the cosine of 55 here and the sine of 55 here. I just prefer to work with angles with respect to horizontal.